So, good afternoon, everybody. Thank you for joining today for our webinar covering the mechanical inspection, a deep dive into ultrasound use for rotating assets. A few more people are still just joining in, so we're going to get started. It's now 2 o'clock UK time, so hope you are all well, and we can now start the webinar. My name is Christopher Hallum. I am the UK and Ireland manager for UE Systems Europe. My contact details are on the screen here. If you wish to ask any questions or get in touch with me in the future, I will also have my contact details on the screen at the end of the presentation also. A few housekeeping rules. This is being recorded, and if you have any questions, please feel free to send me a question in the chat group. There are going to be a lot of people participating today, so if I can answer your question during the webinar, I will. If I cannot, I will get back to every question asked after this via email. So, a little bit about UE Systems first of all. UE Systems was founded back in 1973. We are a company that manufacture airborne and structure-borne ultrasound instruments, along with software, sensors, and also training. We're not a service provider, we are a manufacturer. We give the tools and the support and training to help those that need it. Our main headquarters is in Elmsford in New York. We also have continental regional headquarters around the world. Being part of the UK and Ireland, we come under the European headquarters based in the Netherlands. From the European division, we also have direct relations in the UK and Ireland, Germany, France, Spain, Poland, Italy, and Eastern Europe. So that's UE Systems and myself. So let's actually start with today's topic. So when we're looking at using predictive technologies, we're looking at using a method called condition-based maintenance. And the long-term goal of utilizing condition-based maintenance is to use technology in order to identify potential equipment failures on an early stage, while trying to eliminate unplanned downtime. So in order to reach these goals, we need to start with some form of trend analysis and data collection. The more data we can collect, the more we can analyze, and the more we can have a better idea of how things are occurring on our site. So by implementing our CBM practices, our condition-based maintenance practices, it will help the user with the tools and the software to identify potential or predict immediate risks on their site, but also improve the lifespan of their equipment and hopefully remove or eliminate unscheduled downtime, about keeping that availability for our assets there when it's needed. So many of you would have seen this chart, the DIP to F curve, mentioned on many sorts of platforms, discussing the ways in which an asset is installed and when it starts to run. It's installed with precision tools and technologies, and then at some point along the line of it in its lifespan, it will start to give some warning signs that there's going to be a problem in the near future. And we have different ways and different technologies that we can utilize to help us pick up or detect potential signs of an imminent failure. The good thing with ultrasound is that we can use it as a proactive tool when it comes to lubrication, improving the way we do our lubrication practices. And we can also use it then to detect very early stage change in the way it's working. So we can pick up those things and hopefully highlight them and remove the need for any catastrophic failures. So why ultrasound? So all rotating assets will produce friction, and this friction in turn will generate ultrasound. So with ultrasound, high frequency sounds is something that we cannot hear as human beings. So to be able to pick up something very early, we can detect a change in state. Doesn't mean that it's going to fail imminently, but it's that indication, that early indication of an impending problem. Ultrasound is also non-intrusive. We do not have to change the way our assets are operating for us to collect the data. We can collect the data while it is running live. And at the same time, it's a quick technology to collect the data with. We only need to test one point of an asset at each time we take the readings. So we can do it nice and quickly. By doing all of this, we can improve our lead time for things like planning, for spares, and things like that, because we don't need to have a storeroom full of spares that might or might not be needed anytime soon. Because of the early detection rate of ultrasound, we can then plan, order in our spares, improve our stocks to make sure that we can find the right time to do the corrective actions. By doing this at an earlier stage, it improves the cost and time to repair. So what could actually be highlighted at an early stage as an increase in friction could be something as simple as applying grease, but if not detected at that early stage, could evolve into a much deeper problem. So some considerations to think about when inspecting and trending bearings before we execute any inspection program. We have to have enough adequate knowledge on the subject test equipment, on our assets. If we don't understand how our assets work and how they behave, how do we expect to understand what the data is telling us when we take those readings? We have to be consistent. We need to be consistent. We need to have the correct frequency with which we're monitoring our assets with our technology. We need to make sure that the modules that we're using are the same each time. And we need to ensure that our test location, our test point that where we collect our data from is the same as well. We need to establish an operative baseline so which we can start looking and trending and comparing our data over time. We can also compare readings where necessary. If we have like for like assets on site that can run at the same characteristics, so we can compare to get a better understanding of them. So some of the basics with ultrasound, we need to understand those first. And because we're using ultrasound, high frequency sound, and we're heterodyning the source of that sound to make it audible, we need to understand what is good and what is not so good. So if we have a bearing in a good state, if we think about a newly installed bearing that's adequately lubricated, the sound should be smooth and uniform in nature. It should be nice sound like white noise. But if it's not so good, and again, this is using our human hearing and making our judgments, we'll start to hear maybe sporadic crackling noises or coarse grinding sounds, again at an early stage. An example here of a good bearing would be what it sounds like here. Smooth white noise is what we would expect to hear. When we have an early stage bearing failure, like I say, sporadic crackling noises, this is what we may hear. At this stage, the level of damage is very minor because the sound is not repetitive yet. So not all of the rolling elements might be actually impacting with the damaged area. So it's a nice early indication that there's a problem. And then when we get to a more severely damaged bearing, it might sound even stronger in amplitude, decibel value, and the tonal quality can also change here. So we can quite clearly see the difference there between a good bearing, a bearing in its early stages of a problem, and another bearing there with a more severe problem occurring. We also need to think about what frequency are we setting our ultrasound equipment to when we want to do these inspections. So we're using structure-borne ultrasound. We're listening to the ultrasounds trapped in the structure. So we're going to listen to our high-speed assets or our standard rotating motors at 30 kilohertz. And for then our slow-speed applications where the level of energy being transmitted is a bit lower, we would lower our frequency to around 25 kilohertz to do our inspections to get the good quality of sound. And we need to remember consistency is key to good data. It's very important when using predictive technologies that we have our consistency. So there are different approaches to the use of ultrasound when utilizing this technology for mechanical inspections. We have a few different methodologies, and I'll go over them here now and then go into them a bit deeper once we actually move on with this. So we have the troubleshooting method, we have comparative inspections, and then we have historical trending. And as a site progresses through the use of ultrasound from the start, they will implement all of these types of approaches at some point or another, eventually getting to a point where they'll have historical trending being used, which is normally the preferred approach for us to understand what's going on. So, the troubleshooting method. One of the simplest approaches utilized in the early stages of any sort of program, because we all have to start somewhere. And like you would when you walk through a plant and you're listening for sounds audibly, we're doing that with ultrasound, but at an earlier stage because of the high frequency. So we're going to be hopefully picking things up at an early stage. So this is where we're doing some random testing of equipment. You know, we're troubleshooting, we're popping in and out. Maybe somebody has told us that something doesn't quite sound right to them. So there are some key things we need to understand here. And that's, first of all, is tonal quality. What does the bearing sound like? We've just discussed there how a bearing should sound, what maybe an early indication could be, and what a more severe indication of tonal quality can be. So we need to understand the difference and understand what are we listening for. We need to remember these frequencies again for what we need to inspect at. We're using our contact approach with our modules. And if we have the ability to perform a sound recording on our device, then that may aid us as well, because as we are troubleshooting, you might want to get a second opinion from your colleagues. If you have the ability to sound record, you can play that back on the software, and you can then have a peer review on what your thoughts are with this. And if in doubt still after this, then you can move on to maybe comparing it with a like-for-like asset on your site, which will bring us on to shortly our next methodology. But first of all, I want to give a couple of examples that we have had when we have done some simple troubleshooting on some assets. So the first one was a motor drive end bearing inspected driving a pump. Now, as a troubleshooting approach, we understand we expect to hear a smooth, uniform sound. So what we can do is take a reading, take a sound recording, and make a judgment. So this bearing here, this motor here, you can see from the image, the decibel value was 61 decibels, our frequency was 30 kilohertz, and we took the sound recording. And this is what it sounded like. So as we can hear from that sound, it was non-uniform and coarse in nature. As we can see from the ability to take a sound recording, we can see from the time waveform that the sound does not look smooth and uniform. We can see very large amplitudes and impacts in the time series. In the FFT side of things, we can also see harmonics. And we can see harmonics in this recording at approximately 75 hertz. Now, for a troubleshooting perspective, we can already gauge that there's something not right with this bearing. If we had a little bit more information, like the rotational speed, the type of bearing and the number of rolling elements in there, we could make a further diagnosis as to what is actually occurring. But for the use of ultrasound's purposes, we've identified here that this motor requires further investigation. When the site at the time decided to take this offline and do an inspection, they took it apart and the bearing fell apart as they removed it. It was in a serious state of failure. So a good find using troubleshooting method. The next troubleshooting task that we took part in recently was looking at a planetary gearbox. So These planetary gearboxes have a lot of moving parts inside them, with the shaft, the sundial, having the planetary gears moving and rotating around all at different times. So there's a lot of moving parts going on, but trying to understand what is going to happen. In this instance, the image you see at the top is just an example of a planetary gearbox. The one we inspected on the output section of the gearbox, where there were 4 planetary gears. It was a slow speed application, so we needed to understand, first of all, the operation of the gearbox before we can understand what sort of sounds we're going to hear. It should be, in an ideal environment, if it's good and working well, a smooth, uniform pattern of sound with slight modulation in amplitude as the gears move past the sensor. So we have the sensor on the on the body of this gear, and as a planet rotates through where the sensor is mounted, the sound will increase and decrease. So we should hear some slight modulation. Because it was a slow speed application, we set the frequency to 25 kilohertz to get the best quality of sound. So the sensor, as I said, was on the body of the output stage. So from the sound recording, this is what we could pick up. So what we can hear here is a very repetitive sound. As you can see from the time waveform, we see large amplitudes. And as we hear the increase in amplitude, you hear what sounds similar to a crunching sound or a very high friction sound that's highly repetitive. Now, bearing in mind that these planets are rotating at 60 RPM, so we're going to get some form of modulation anyway, but we should not be hearing that level of friction. So you hear this sound and we decide there's further investigation needed, as it is not a sound you would expect to hear. So as I said, the output stage was at 60 RPM. There were 4 planet gears in there. So what we started to see from the time waveform image was that we had modulation of amplitude every 200 milliseconds. So every 200 milliseconds, we would get an increase in amplitude, which would correlate to 4 planets rotating at 60 RPM. So as we can see here now, a zoomed in version of the time series, and we can see that every 200 milliseconds, we have an increase in amplitude and a steady decrease as the planet rotates through where the sensor is mounted. If this was physical damage, as repetitive as it was, the impact in sound would be shorter and more abrupt in duration, and potentially would give us more of a fishtail inspection on the time waveform. This sound is more of a friction-based sound from our analysis, from listening to the sound. And I will just play it again for you. When you listen for the increase in amplitude, the scratching / crunching sound you hear. So you hear, when we get to that increase in amplitude, we hear the crunching sound, which would, under experienced ears, sound like an increase of friction. So the first check to suggest would be lubrication, because lubrication relates to friction. So at the time, it had come to light that the asset had been recently refurbished and had been in operation for a few weeks. So the oil was inspected. The oil was blackened, and after further investigation, it turned out that this was not the oil that had normally been used. So the first simple bit of rectification work that could be done could be to actually clean the system and replace it with oil that had been previously used, the correct type of oil. So we then returned to take another sound recording once the correct oil had been applied. And this is the sound that we heard next. we can now see that we have a much more improved sound quality. It is more smooth and uniform with very slight modulation sounds. To me, this highlights the importance of having the correct lubrication within your assets and the difference that it can make. The fact that this was picked up at an early stage means that the asset health and the lifespan of this asset now will be hopefully closer to its designated lifespan as it should be. So, going on to the comparative method, as we said, when we're troubleshooting, if we're not sure about something, then let's see if we can compare it with a like-for-like asset. So this is a good method to execute when trying to understand a level of condition if we have multiple assets that are the same. It could be used to help us rank our like-for-like assets in level of health, as long as certain parameters are met. So for that to happen, we need to have our assets like for like. So for example, the same manufacturer with the same type under the same speed and load conditions. It's very important for us to be able to have that to make a comparison. And we also need to make sure the same test point is met on every point that we check. Again, quality data to compare it with. We need to ensure that we have the same settings on our equipment also, so that we can compare this data. Consistency is key. And we need to remember those frequencies again. I know I'll repeat them because it's important that we have our frequencies set for 30 kilohertz for standard speeds and 25 kilohertz for slow speeds. And we are using the contact approach for mechanical inspection. If we have the ability to do sound recordings, we can then use this on the software to superimpose each sound recording to compare them like for like, because you may have a very slight difference in sound quality that you want to check. So I want to go through a few examples of how you can utilize the comparison method. So as I was saying, we're trying to understand the condition. Comparing even a decibel level can help give us an indication to investigate further or what we need to look at, because a rise in decibel level indicates a change in state. So if we have multiple assets, we can do this quite comfortably. So for example, in this image here, we have 6 motors that are all the same manufacturer, speed and load. We can test all of our bearings on these, and out of the 6, all of them were within 3 decibels of each other except one. One of them was 12 decibels higher than the rest. So this is a good indication of something that is different from the rest. So we might decide that this one asset we would investigate further while leaving the others as they are right now. So just a simple indicator for using the comparison method just by checking the decibel value. So this is another case study that we came across in the recent past, where we were looking at a cable twisting machine, a multi-core cable twisting machine, where we have idle rollers that feed in smaller cables into the one cable to manufacture a multi-core cable. You can see this is an example image of the type of asset, but we were looking at the idler bearings, the ones that are looped in red. They were sealed for life bearings, simple to change, but if they fail, then it causes a problem on the production of the cable. So it's still important to be able to check them and understand which ones need to be repaired or replaced in which order. As they are like for like, under the same speed and load all the time, we can utilize the comparison method at the first point of inspection to see which ones are in what condition and what work might need to be used. So on this particular cable twisting machine, there were 5 idler bearings. So we can take sound recordings of each of these bearings, record it, and then compare them and see what they are like to where they are in their health. So Bearing number 1 was inspected, and this was the sound recording for bearing number 1. As we can hear from that, pretty smooth and uniform in nature. So this is a good start. Idle bearing number 2 sounded like this. So by just looking at comparison now between number 2 and number 1, we can see more repetitive impact, higher amplitudes. So now we can start to determine that number 2 is in a worse state of health than number 1. Number 3 idler bearing was taken, and this was the sound recording for number 3. And as we can hear from this one, bearing number 3 was actually a little bit more worse than bearing number 2. So we're still now starting to understand which of the bearings are in what condition. Bearing number 4 was taken, and this is the sound recording for number 4. Oh no, I hear you say, it's just getting worse, and you feel sorry for the operator at this site. As we can see, number 4 is looking a lot worse than any of the other bearings. So you're starting to think now, wonder what number 5 is going to be like, because that's going to be worse. Well, this is what number 5 sounded like. Fantastic, I hear you say. It sounds fantastic. A very smooth and uniform sound. We can see from the time waveform that it is lovely and smooth with no amplitudes. So now looking at all 5 of those idlers, we can start to see how they're behaving and where they are in their health and which ones might need our attention. So this is just using the time waveform analysis. And just by looking at these, I bet you can get that number 4 is probably the one that we need to be really concerned with right now. What we can do with this as well is take these recordings into the FFT and look at the base level of sound. And as we can see from this, that bearings 1 and 5 were pretty good. Bearings 2 and 3 were in a degraded state. They were not really that good. They were showing good signs of a potential problem. But bearing number 4, as you can see from the yellow trace at the top, is a higher decibel value and the one that we need to be concerned about. So this is a great way to utilize the comparison method to actually help us gauge the health of our bearings. So we've started troubleshooting, we've started using a little bit of comparison method, and we're starting to get an idea now of how our assets work and what we expect to hear. So now we can utilize software to create asset lists and routes on up for our probes where we can start to collect data and start to historically trend this. So the historical approach is probably the most preferred method for a mechanical inspection program with ultrasound on a site, because we get to understand the health of our assets over a period of time. So this allows the inspector to trend our asset decibel values and tonal qualities over a period of time. It enables the user to set baselines and alarm levels, and I will cover those two subjects shortly. We get to understand the characteristics of our assets. We can actually understand how they behave by the way that they talk to us. And if we're collecting data over a period of time using this software, we can then create reporting documentation that will help us with our justification for remedial work to take place. And if we're doing this historical trending, we can help improve the way that we do our lubrication intervals and our lubrication program by understanding the condition. So there are some key things to have in place when implementing the trending method, the historical trending method. Consistency is key. Having marked test points, making sure that the frequency setting is the same every time, making sure that we use the same modules each time. Have we performed a criticality analysis study of all of our assets on site so we understand how often we will want to collect our data, and maybe if they are critical enough, do we want to be using 24/7 remotely monitored equipment to help keep track of the condition of our highly critical assets? It's an important thing to consider. We then need to go on to setting our baselines. And once we've set our baselines, we can then look at setting our alarm levels. And when we start to collect our initial data, like our baselines, for example, we will have a decibel value, but hopefully we can take sound recordings with the device that we have, so we can have something to reference to each time we take a reading. It's always good to be able to refer back to something or a recording if you haven't inspected it for maybe a month or two. Is access an issue? You need to ask yourself. Can I get access with a man-portable device? Do I need to install remote access sensors to help me with my program to collect that data each time? So one of the most common questions that we get asked when we're looking at the historical trending method is, how do I set my baselines? Well, there are a few ways in which baselines can be set. It is very much up to the inspector creating the program as to how they go about understanding what baselines to set. We first need to understand that the important thing is what is a good sound against a bad sound. And as we've been discussing, it's that smooth, uniform sound that we want to hear. And we can use a troubleshooting method or a comparative method to help us understand if it is good or not so good. So in an ideal setting, a newly installed bearing on an asset would be our go-to baseline. But we live in a real world and we live by that, so we want to install our baselines on assets that could be a few years old. So another way we could do this is looking at an average decibel if we're checking like-for-like assets. If we're also checking like-for-like assets, we could decide to take the lowest decibel out of a lot of them as our baseline. You could even take the first reading that you come to. Maybe look at applying some grease if you can, to see if you can improve the quality of the sound to as low as possible. It's very much up to the inspector as to how they want to go about setting their baselines. The thing about baselines is that if you have an invalid baseline, or one that's in a degraded state, for example, it will quickly present itself to you. Because once you start collecting historical data, you will see the decibel value begin to rise over time. And it will continue to rise because it's already in a degraded state. So even if you do make a mistake with a baseline, you will highlight this as you collect more data. So once you've set your baselines, you need to look at setting alarm levels so that you can notify yourself of when certain conditions are met. And these action levels for the alarms have been determined over many years of inspections. And we've set our baselines, and these next values are numbers above the baseline value. So the first baseline level is alarm level is 8 decibels above the baseline. This could be classed as a low level alarm, and it might be something as simple as requiring lubrication. What we might see here is a smooth uniform sound that has just increased in level of sound, which highlights to us a lubrication issue. Once we start seeing levels of 16 decibels above the baseline, we're going to start to see some form of very small minor damage occurring within the bearing itself. And this would be maybe classed as a high alarm. If we get to the point where we're starting to read decibel values that are in excess of 35 decibels above our original baseline, This is indicating to us that we have a pretty severe failure potentially occurring, and we need to do further investigation or work quite soon. I've had experience with these sort of alarm levels, and I have seen it at baselines above 39 decibels above the baseline, and we see failures a few weeks later. So it does happen, and these are valid. So with historical trending, I want to share with you now some examples of a real-time historical trending ultrasound program from a user that uses this technology. So one of these here is a chiller water pump looking at a motor drive end bearing. We can see from the data here, we have over 1 year's worth of data points collected. We can see from the historical chart now that the baseline was set and was steady for a long period of time. But as you can see then, over a shorter period of time, we start to see a steady climb in the decibel value. But we have not quite hit a low alarm level yet. So this shows to me that the bearing now is getting closer, requiring some lubrication, because the level of lubrication is now starting to reduce. The friction is starting to increase. So it gives us an indication that something's coming along here, and we might need to do something soon. With the same program, we had another motor drive end bearing being inspected on this site. We had another year's worth of data, where we can now see a little yellow highlight there, a low level alarm being indicated. So the baselines were set, and as I said to you, when you have a good baseline, it will stay steady for a long period of time. But as we can see, it started to climb slightly, and then all of a sudden we see an increase to 8 decibels above the baseline, which indicates a low level alarm and some lubrication may be required. The inspector on this site told me they discovered this lower level alarm, and they did some rectification work. And as we can see afterwards, the baseline has returned back to low level again, and we're running nice and smoothly. Great way of using historical trending. So the next one being a motor drive end feeding a pump. With this, we have another year's worth of data, and as we can see now, we're starting to see a few more colors on the chart, indicating that we may be seeing a problem soon. So the baseline was set and was steady for a period of time, and as we can start to see the decibel level increasing over time. We can see from the baseline and from the time and out time waveform we see on the screen there, smooth and uniform to begin with, and then it started to increase. We hit the low level alarm first of all, lubrication applied, but the sound does not return to the baseline, but does reduce slightly. But then we see after we've lubricated, the sound starts to increase again and carries on to continue increasing, which tells us that it's not a lubrication related problem anymore, it is a physical problem actually occurring. So now the work orders need to be raised to take further action. But a great example again of how to use historical trending to help us with understanding the health of our assets. So once we've actually got some historical data and we're starting to look at improving the way we're doing things on site with condition-based maintenance, we can utilize other forms like lubrication to improve utilizing this same technology. So when it comes to lubrication, there are a few ways in which programs can be executed. So the most commonly used one would be a time-based preventative maintenance task, where we have a set time and schedule for just applying the grease. So the next one would be advancing it on slightly, where we can do a time-based preventative maintenance regime for applying lubrication, but using ultrasound alongside us. And then in a best case scenario, we can do condition-based lubrication from our historical trending. It's kind of trying to find ways to remove maintenance for maintenance sake. Do we need to lubricate those bearings all the time? Does it need it? So Even if we don't have historical data on our plant, we can still use ultrasound to help us with our lubrication practices. The focus is on bringing the level of friction down with the application of grease. So as we know, friction produces ultrasound. So as we get an increase in friction, we start to see an increase in ultrasound. So by applying grease again, that friction will reduce and the sound should go down. And a common question that I sometimes ask the sites is, when do you actually know when you have applied enough grease? And the most common answer I seem to get, even today, is I don't know. But when I see grease coming out of the side, I think that's enough. Which is not really the correct answer, is it? We all know that nowadays. But it's still a common answer I still see today. So let's think about ultrasound, a time-based PM assisted by ultrasound. So what we can do here is you have a set frequency of application, so how often you go about applying grease to your assets. Normally that PM will tell you how much grease to be applied. And my normal questions there is does the bearing need grease at that time that it stipulates? How do we know that? And if we are going to apply that amount of grease, how do we know that that's how much we need? And this is where ultrasound can help us with understanding this. So if we apply grease, we will reduce the friction, in turn reducing the decibel value. So that's what we're looking at trying to achieve. Applying the grease will remove that level of sound. So we apply the grease until the sound doesn't go any lower. But if we apply grease and the decibel level increases, then we need to stop applying the grease because now we are seeing signs of over lubrication. And this is an example of a sound file of a bearing being lubricated. So as we can hear there, and as we can see from the time series waveform, a large level of friction and ultrasound being generated. As the grease applies, the sound becomes a lot smoother and lower in decibel value, and it doesn't go any lower, so we stop applying the grease. A good way of utilizing ultrasound to help us with our lubrication practice. So how about moving it on to the next stage and looking at doing a condition-based lubrication program? So with this, we're starting to look at our historical trending. So we would have our baselines taken for our assets, we will have our alarm levels set, and then once we get to a low level alarm, that could be our indication we need to apply grease to that asset. We then start to listen while applying the grease, applying it until the baseline is met or we are as close as possible on that. One question you could also state is that if I set my baseline and the baseline is 20 decibels, for example, and I have a PM that tells me to go back out and lubricate that bearing, and I go back there and the reading is still 20 decibels and it's smooth and uniform, do I need to apply grease? Does that bearing require grease because it is still the same level of sound as it was 3 months ago, for example? We're doing condition-based lubrication, not just because we think it needs it, we're doing it because the bearing tells us it needs it. So this is a good way of using ultrasound for condition-based lubrication. So moving on to slow speed bearing applications, an area where ultrasound works very well. So a slow speed bearing produces less or lower levels of friction, in turn providing lower levels of ultrasonic emissions. This, however, allows the inspector to actually perform good inspections to identify early problems in tonal quality, for example. So this is where we will not necessarily use the same sort of alarm levels as we would in a high-speed bearing because the level of friction is much lower. So we're now going to focus on what is the tonal quality of the bearing, looking at time waveform analysis more than anything else. 0 decibels can be an acceptable baseline. Due to the low levels of friction, you may get on your display 0 decibels, but you can still hear the sound. So you still can do sound recordings for the comparison method for trending. You can have faults that can occur at just 2 decibels above the baseline on slow speed bearings. And one of the examples we have will show that. So what we want to do on the slow speed bearings is look at what level the baseline is giving to us and then adjust our alarm levels accordingly. We want to narrow those alarm levels. Having the ability to do sound recording on slow speed rotating equipment is very advantageous. It gives you the benefit of looking back at the tonal quality after you've done the inspection. And then you can use that for a comparison method, for example, in historical trending. So an example of a good slow speed bearing. The amplitude is much lower in sound, but it is smooth and uniform. Now this is a comparison with a bad slow speed bearing. As we can hear now, the tonal quality has changed dramatically. So we now gauge the tonal quality, we can hear that, we know that there's a problem occurring. So a quick case study on a slow speed bearing application, looking at a large oven dryer, relatively new, but it was a slow speed application, large dual rolling element bearings. 6 months into operation, there were 8 large bearings to inspect, and they were on the same speed and load and type. So this was the first time inspecting these bearings, and because they were all like for like, we could utilize one of our methodologies, the comparative method, comparing like for like. So 7 of the bearings, out of the 8, 7 of the 8 registered 0 decibels on the screen, but you could still hear the sound, and this is what they sounded like. Smooth and uniform in nature and very low amplitude. So that is what we would expect to see. And that can be our suggested baseline. Smooth, uniform, 0 decibels, no impacts, perfect. One of the bearings registered 2 decibels. Not a very high number, I hear you think, but that is a 200% rise on the other 7. The sound recording was slightly different. This was no longer smooth and uniform. We could quite clearly see repetitive impacting sounds. This indicates that this bearing is in a state of failure. This is a severe change in the tonal quality. So the site decided to remove this bearing or schedule the replacement of this bearing. After they took it out of situ, they sent me pictures of the damaged bearing. As you can see from the images, there were some severe cracks. Part of the outer race fell off, the cage inside had damaged, and one of the rolling elements had moved 90 degrees. So this was a great find. A good way of identifying a problem at an early stage. It would have failed dramatically at some point, but we caught it early enough to actually get the work done and do it in a scheduled way. So in conclusion, Ultrasound can be a quick and simple way of helping an inspector gauge the level of condition of their assets at an early stage. You could see ultrasound as the doctor that's confirming that something is not right with your assets. And ultrasound can lead you to then implementing other CBM technologies to help you with your diagnosis of potential failures, be it technologies like vibration analysis, oil analysis, motion amplification, but understanding that not one technology is going to be the cure of all evils on your assets. It's about having not more data, but about good quality data. That is the important thing here. I would like to thank you all for your time today, and I hope you found this informative. And if you have any questions, please feel free to either email me on my email address at chrish@uesystems.com. Anytime, I'll be happy to answer those questions. You can also visit our website where we have a learning center that has free to access tutorials and guides. Our next webinar coming up in the next few weeks will be looking at energy conservation using ultrasound to improve your plant's energy efficiencies. But I will leave the chat group open for the next few minutes if you would like to send any questions through. I will answer a few as I go through now just to see if there's anything I can answer straight away. So one of the questions is there a difference between early stage bearing failure and a lack of lubricant within a bearing? So when we have a lack of lubricant in the bearing, the sound will still sound smooth and uniform in nature. It will just be a higher amplitude than it was previously. Early stage bearing failure will be sporadic, impacting, crackling noises. So have we got a reference on situations when a pump handles different viscosity fluids and the loads therefore vary on a wide range? So if you are looking at maybe motors that are on variable frequency drives that are changing in speed, what you would do there is have a wider alarm level set, because what you'll have is an increase in speed which will have a slight increase in friction, which will in turn give a slight increase in decibel value. So you would want to make a note maybe of what material or medium is flowing through, but also what speed it is running at that time so you can compare. So a question about utilizing ultrasound for detection of problems in wind turbine gearboxes, broken teeth, planetary stage bearing damage. So yes, we have seen this has been proven very successful. We do not do the inspections ourselves, but we do help a lot of service providers within the wind farm energy sector. And because it's such slow speed, you can really hear the change in tonal quality when you start to have damage occurring. So yes, it is very successful in the use of that. So how to do the correct measure of sound? So we're using the contact approach. So what you want to do is place the sensor or the contact module as clear to the point where the bearing is housed, on the bearing housing or on the motor. That's what we're trying to do when taking a reading. So there another question about ISO standards for dealing with decibel levels for machinery. So this is very much talking about in relation to like vibration analysis and ISO standards. With ultrasound, we're only dealing with the level of friction in a bearing. So, and that can be for any type of bearing. So there is no ISO standards for that. It's all about collecting your baseline level and then trending or comparing over time. So what kind of sound will there be if there is partial discharge due to harmonics by the VFD? So if you're talking there about fluting, electrical fluting. What we may see is we might hear a not necessarily a smooth uniform sound, but a more coarse, rough sound. And what you would see if you do a sound recording is harmonics relative to the electrical line frequency. So, for example, in most of the world, you might see 50 hertz harmonics. In America, you may see 60 hertz harmonics that can identify an electrical based sound there, and you wouldn't expect to see that. So, some questions about obviously having access to this. There will be a copy of the presentation recorded on our YouTube channel, and get in touch with me if you would like a PDF copy of this presentation also. So, a question about electrical discharges in bearings. Yeah, I think I've just covered that one. You start getting the harmonic frequencies of electrical discharge. That's the big indicator. When the bearing is in a loosened condition. So if the bearing is in a loosened condition, what you're going to get then is a non-uniform rotation. It's going to be more concentric circles. It'll increase and decrease. So it'll almost be like a warble sound. And that could be relating to an imbalance or a misalignment or something that's loose because it's no longer rotating in a circular fashion. So can the ultrasound be affected by nearby equipment in a noisy environment? So what you're looking at with ultrasound, it transmits from its source, but is trapped within a solid structure when we're talking about bearings. So the only sound you're going to pick up is any sound connected to that structure. So maybe if you're looking at a shaft bearing, you may get sound picked up from other areas on that shaft, but the sound from ultrasound is strongest at its source. So if you hear the same sound on different test points along a shaft, wherever that source is strongest in decibel value is the source of your sound. What else can ultrasound be used for to monitor in CBM? So what I would suggest there is if you go to our YouTube channel, my previous webinar discussed all of the basic applications of ultrasound and all the areas that it can be utilized for. It is a very versatile technology. So what is the benefit over vibration for CBM? So what I would say in regards to that is ultrasound does not replace vibration. Vibration does not replace ultrasound. They both have similar principles of operation. It's just that with ultrasound, you are going to get a slightly earlier detection rate. And also, when we're talking about the differences, the advantages, I would say ultrasound is beneficial when it comes to the slow speed applications. Most vibration programs will be very extensive, but maybe miss some of the slower applications. And that's where the two technologies can be really, really complementary with each other. And you may take ultrasound to be added to your vibration program. And when you then get a ultrasonic alarm, check it with your vibration to see if the vibration is picking anything up. That could give you an indication as to where it is on that P2F curve. So ultrasound techniques in pipelines. So if we're talking about leak detection, then yes, you can use it for that. So again, another question on ISO standards for dB levels. There are no ISO standards for decibel levels because there's so many variables with speed and load and the type that will change the value of the decibel. It's all about trending the value of the decibel. So what type of ultrasonic kit is used? All of these case studies were used using the UP15000 tool. Again, you can get all information on our website with regards to the different types of probes. What could cause a new bearing to fail even without load? Normally, we would then talk about things like installation. The installation method and how it was actually installed can cause problems at an early stage, but we can again listen to that when we do those. So shouldn't readings be taken in the load zone for preference? Again, this is a vibration analysis type of question, but with ultrasound, it's about taking the reading from the same point every time. So it doesn't have to be the load zone. So you can take it for consistency from one point each time, and then you can trend that. What I would suggest on maybe larger bearings, though, is maybe looking then at the load zone area for just a reference on a large slow speed bearing, for example. So when a bearing is over greased, how do you reduce it to the baseline? Pretty difficult without having to really remove that grease, have that grease removed. So that's the key thing here. When applying grease and you hear the decibel level increase, you need to then look at stopping your greasing and leaving it as it is. Applying more will just cause a problem. So that's the hour up of our webinar presentation today. I do see there are lots and lots of more questions being asked. I will take a copy of the chat group. Any question that I haven't answered yet, I do apologize, but over the next few days, I will answer all of your questions via an email, and you can send your questions to me via my email address too. Tomorrow is a UK holiday, so I may not be in the office all day, but I will get answers to all your questions in the next few days. So I would like to thank you all for your time today and wish you a good weekend coming up.